So we learned about standard enthalpy change for a reaction. Delta H with this degree symbol for the reaction. So that's the change in enthalpy when all the reactants or products are in their standard states. And so here is a reminder of what standard states are. So for a gas, standard state is the pure gas at 1 atmosphere. For a liquid or solid, it's the pure substance in its most stable form at 1 atmosphere and the temperature of interest, which is generally room temperature, which is considered to be 25 degrees Celsius. If the substance is in a solution, it's a concentration of 1 mole per liter. So the standard entropy change for a reaction, delta S for the reaction, the little degree symbol, that means it's standard, is the entropy change for a process where all the reactants and products are in their standard states. Entropy is a state function. It doesn't depend on how you got from point A to point B. So the change in entropy is equal to the standard entropy of the products minus the standard entropy of the reactants. So we need to define what this is, this S with a degree symbol. That's standard molar entropies. So that would be per mole of substance. Well, for zero, we defined, we kind of picked a zero, right? Because absolute values of enthalpy can't be calculated, so just like with elevation, we chose sea level. For enthalpy, we chose the elements in their standard states as being zero enthalpy. But for entropy, there is an absolute zero. And so the third law of thermodynamics is that the entropy of a perfect crystal at absolute zero is zero. So temperature is a measure of the average kinetic energy of a substance. When the temperature is zero, the atoms in the substance are not moving, they're not even vibrating. There is no motion, right? And they are ordered in their crystal. They are as ordered as possible. Their entropy is zero. There's only one way you can have the pieces, and this is based on Boltzmann's definition of entropy, which was that entropy is equal to a constant times the natural log of W. So here the W is 1, which is 0. So there we go. So entropy is an extensive property. It does depend on how much stuff there is. So we can't just say, 5, right? It has to be scaled for the amount of stuff. So molar entropy is the amount of entropy that 1 mole of that has. So these are standard molar entropy values at 298 K, which is 25 degrees Celsius room temperature. We're not going to see any zeros here because 0 was at 0 Kelvin. But these are all calculated relative to that. So we can look up the entropy per mole of different substances at different temperatures. Well, here it's at the 1 temperature. So at 25 degrees C, standard entropy of any substance is the energy dispersed into 1 mole of that substance. And it's going to depend on how many places there are to put the energy. And that's affected by a whole bunch of things. The state of the substance. We saw, translational motion, rotational motion, vibrational motion. That changes with the state. It's affected by the molar mass. The particular allotrope. An allotrope is a different form of an element. So carbon takes several different allotropes. One is a diamond and one is graphite, right? They have different properties. The molecular complexity of what you're looking at is going to affect the standard entropy and how dissolved it is, the extent of dissolution. So there's lots of different things that affect the standard molar entropy. Standard molar entropy of a gas generally larger than that of a liquid, which is greater than that of a solid, because gases have more places to arrange their components, more places to put their energy. And so if we look at liquid water and water in the gas state, we see that the entropy of water in the gas state is higher. Did he get locked out?
Yeah.
This is another thing I forgot to do. No worries. Yes. So we can see a pattern with the noble gases and the entropy. So looking at them in order of increasing mass, the size of the atom is increasing, and we see that the amount of entropy is also increasing. The reason for this is that the energy states associated with the motion of heavy atoms are more closely spaced, which allows for more dispersal of energy. This trend only holds if all of these are in the same state. Here's the allotropes, graphite and diamond. The entropies are different because the arrangement of the atoms is different. So a diamond has lower entropy than graphite. Graphite has carbon atoms that are less constrained. It forms a two-dimensional structure where the carbon atoms are covalently bonded to each other. But between those two layers, the layers are just held together by intermolecular forces, and so they can slide relative to each other. In a diamond, we have these covalent bonds going in all three directions, and so there's very little opportunity for them to move. So this is not zero, but it's a small number. If we look at molecular complexity, entropy will increase as molecular complexity increases. So we can demonstrate this by making a comparison between these two guys. Their molar masses are close, and so we're not expecting a big difference in entropy because of that. But nitrogen monoxide is a molecule, whereas argon is an atom, right? And so here we have translational motion, rotational motion, and vibrational motion, where the bond can actually vibrate, stretch, and contract. So there are more places to put the energy. We can look at ethene and carbon monoxide, molar mass almost exactly the same. But C2H4 is more complex. We've got carbon bonded to oxygen, or here we've got Well, it really doesn't matter. It's one of those days. It's two atoms bonded to each other. But here we have 5 different bonds, and those bonds can all vibrate. So we see that ethene has a higher entropy than carbon monoxide. If we look here, where we have molecular complexity increasing and the mass increasing, we see that the entropy also increases. So there are trends in entropy.
Professor?
Yes?
So it's related to the stability of certain molecules that are extremely complex. So
It's related to how wiggly they are. So the more parts, the more opportunity for vibration, right? And I mean, you compare nitrogen monoxide and nitrogen dioxide, they both have translational motion, they both have rotational motion, but nitrogen dioxide has 2 bonds that can stretch and contract, whereas nitrogen monoxide only has 1. So the more bonds you have, the more wiggling a molecule can do, the higher the entropy. When you dissolve a crystalline solid, that generally increases the entropy. So if we look at potassium chlorate, both solid and in solution, the dissolved form has larger entropy. And that one should make sense, because here we have the ions are going to separate in solution and then they can move around, right? Whereas in the solid state, we don't have the translational and rotational motion for the ions. And another way to think of it is that the energy that was concentrated in the crystal now gets spread out over a larger area, which is also an increase in entropy. So calculating standard molar enthalpies for reactions is just like calculating delta H, because it's a state function. So we're going to look at the entropy of the products and multiply each of them by the number of moles, and then we're going to subtract the entropy of the reactants, again multiplied by the number of moles, the coefficient in the balanced chemical equation. When we did this with delta H, anytime we had elements, their heats of formation were 0. Here we're not going to run into any zeros. Nothing has 0 entropy at 25 degrees Celsius. So let's calculate delta S, standard delta S for this equation. So what we want to do is it's the final things minus the initial things. So delta S is going to be 2 moles times the entropy for water in the gas state. 188.8 joules per mole Kelvin. And then we have 2 moles of SO2, so 2 moles times SO2, 248.2 joules per mole Kelvin. And then we're going to subtract all of that, and then we're going to subtract 2 moles of H2S. H2S is 205.8 joules per mole Kelvin, plus 3 times oxygen, 205.2 joules per mole Kelvin. I think the most common thing that happens when students get a problem like this wrong is that they typed it into their calculator wrong. So you gotta be careful. So 2 times 188.8 plus 2 times 248.2 minus the quantity 2 times 205.8 plus 3 times 205.2. Negative 153.2 joules per Kelvin. For the reaction as written in molar amounts. Any questions? Yes.
So this would be a non-spontaneous reaction, right?
Well, we can't tell just from delta S. Right? Yeah. That would be a good guess that it's non-spontaneous because the change in entropy is negative, but it depends on what happens to the surroundings as this happens. Yeah. Yeah, Chem 1B is a place where we have to start acknowledging some of those messy things about that we just kind of overlooked in Chem 1A.